Now I'm going to give you some sentences or axioms in first-order logic, and I want you to tell me if they correctly or incorrectly represent the English that I'm asking about. So tell me, yes or no, are these good representations? And the first, I want to represent the English sentence, Sam has 2 jobs. And the first-order logic sentence is, there exists an X and Y such that job of Sam X and job of Sam Y and not X equals Y. And so tell me, yes, that correctly represents Sam has 2 jobs, or no, there's a problem. And secondly, I want to represent the idea of set membership. Now assume I've already defined the notion of adding an element to a set. Can I define set membership with these 2 axioms? For all X and S, X is a member of the result of adding X to any set S, and for all X and S, X is a member of S implies that for all Y, X is a member of the set that you get when you add Y to S. And third, I'm going to try to define the notion of adjacent squares on, say, a checkerboard, where the squares are numbered with X and Y coordinates, and we want to just talk about adjacency in the horizontal and vertical direction. Can I define that as follows? For all X and Y, the square XY is adjacent to the square plus X1Y, and the square XY is adjacent to the square X plus Y1. And assume that we've defined the notion of plus somewhere, and that the character set allows plus to occur as a character for a function. Tell me, yes or no, is that a good representation of the notion of adjacency? First answer is yes. This is a good representation of the sentence, Sam has 2 jobs. It says, there exists an X and a Y, one of them is a job of Sam, the other one is a job of Sam, and crucially, we have to say that X is not equal to Y. Otherwise, this would be satisfied, and we could have the same job represented by the variables X and Y. Is this a good representation of the member function? No. It does do a good job of telling you what is a member. So, if X is a member of a set because it's one member, then we can always add other members and it's still a member of that set. But it doesn't tell you anything about what X is not a member of. So for example, we want to know that 3 is not a member of the empty set, but we can't prove that with what we have here. And we have a similar problem down here. This is not a good representation of the adjacent relation. So it will tell you, for example, that square 1, 1 is adjacent to square 2, 1, and also to square 1, 2. So it's doing something right. But one problem is that it doesn't tell you in the other direction. It doesn't tell you that 2, 1 is adjacent to 1, 1. And another problem is that it doesn't tell you that 1, 1 is not adjacent to 8, 9. Because again, there's no way to prove the negative. And the moral is that when you're trying to do a definition, like adjacent or member, what you usually want to do is have a sentence with the equivalent or biconditional sign to say, this is true if and only if, rather than to just have an assertion or to have an implication in one direction. You remember how problem solving works. We have a state space like this, and we're given a start space and a goal to reach, and then we search for a path to find that goal. And maybe we find this path. Now, the way a problem-solving agent would work is first it does all the work to figure out the path to the goal, just doing by thinking, and then starts to execute that path, to drive or walk, however you want to get there, from the start state to the end state. But think about what would happen if you did that in real life. If you did all your planning ahead of time, you had the complete goal, and then, without interacting with the world, without sensing it at all, you started to execute that path. Well, this has in fact been studied. People have gone out and blindfolded walkers, put them in a field, and told them to walk in a straight line, and the results are not pretty. Here are the GPS tracks to prove it. So we take a hiker, we put him at a start location, say here, and we blindfold him so that he can't see anything in the horizon, but just has enough to see his or her feet so that they won't stumble over something, and tell them execute the plan of going forward. Put one step in front of each other and walk forward in a straight line. And these are the typical paths we see. Start out going straight for a while, but then go in loop-de-loops and end up not on a straight path at all. These ones over here, starting in this location, are even more convoluted. It's going straight for a little bit and then go in very tight loops. So people are incapable of walking a straight line without any feedback from the environment. Now here, this yellow path, this one did much better. And why was that? Well, it's because these paths were on overcast days, and so there was no input to make sense of. Whereas in this path was on a very sunny day, and so even though the hiker couldn't see farther than a few feet in front of him, he could see shadows and say, as long as I keep the shadows pointing in the right direction, then I can go in a relatively straight line. So the moral is, we need some feedback from the environment. We can't just plan ahead and come up with a whole plan. We've got to interleave planning and executing. Now, why do we have to interleave planning and execution? Mostly because of properties of the environment that make it difficult to deal with. The most important one is if the environment is stochastic. That is, if we don't know for sure what an action is going to do. If we know what everything's going to do, we can plan it out right from the start. But if we don't, we have to be able to deal with contingencies of, say, I tried to move forward and the wheel slipped and I went someplace else, or the brakes might skid, or if we're walking, our feet don't go 100% straight. Or consider the problem of traffic lights. If the traffic light is red, then the result of the action of go forward through the intersection is bound to be different than if the traffic light is green. Another difficulty we have to deal with is multi-agent environments. If there are other cars and people that can get in their way, we have to plan about what they're going to do, and we have to react when they do something unexpected. And we can only know that at execution time, not at planning time. The other big problem is with partial observability. Suppose we've come up with a plan to go from A to S to F to B. That plan looks like it'll work, but we know that at S, the road to F is sometimes closed, and there'll be a sign there telling us whether it's closed or not. But when we start off, we can't read that sign. So that's partial observability. Another way to look at it is, when we start off, we don't know what state we're in. We know we're in A, but we don't know if we're in A in the state where the road is closed, or if we're in A in the state where the road is open. And it's not until we get to S that we discover what state we're actually in, and then we know if we can continue along that route, or if we have to take a detour south. Now, in addition to these properties of the environment, we can also have difficulty because of lack of knowledge on our own part. So, if some model of the world is unknown, that is, for example, we have a map or GPS software that's inaccurate or incomplete, then we won't be able to execute a straight line plan. And similarly, often we want to deal with a case where the plans have to be hierarchical. And certainly a plan like this is at a very high level. We can't really execute the action of going from A to S when we're in a car. All the actions that we can actually execute are things like turn the steering wheel a little bit to the right, press on the pedal a little bit more. So those are the low-level steps of the plan. But those aren't sketched out in detail when we start, when we only have the high-level parts of the plan. And then it's during execution that we schedule the rest of the low-level parts of the plan. Now, most of these difficulties can be addressed by changing our point of view. Instead of planning in the space of world states, we plan in the space of belief states. To understand that, let's look at a state. Here's a state space diagram for a simple problem. It involves a room with two locations. The left we call A and the right we call B. And in that environment, there's a vacuum cleaner, and there may or may not be dirt in either of the two locations. And so that gives us 8 total states. Dirt is here or not, and the vacuum cleaner is here or here. So that's 2 times 2 times 2 is 8 possible states. And I'm drawing here the state space diagram with all the transitions for the 3 possible actions. And the actions are moving right, so we go from this state to this state. Moving left, go from this state to this state. And sucking up dirt, we go from this state to this state, for example. And in this state space diagram, if we have a fully deterministic, fully observable world, it's easy to plan. Say we start in this state, and we want to end up in a goal state where both sides are clean. We can execute the suck dirt action and get here, and then move right, and then suck dirt again, and now we end up in a goal state where everything is clean. Now, suppose our robot vacuum cleaner's sensors break down, and so the robot can no longer perceive either which location it's in or whether there's any dirt. So we now have an unobservable or sensorless world rather than a fully observable one. And how does the agent then represent the state of the world? Well, it could be in any one of these 8 states, and so all we can do to represent the current state is draw a big circle or box around everything and say, I know I'm somewhere inside here. Now, that doesn't seem like it helps very much. What good is it to know that we don't really know anything at all? But the point is that we can search in the state space of belief states rather than in the state space of actual spaces. So we believe that we're in one of these 8 states, and now when we execute an action, we're going to get to another belief state. Let's take a look at how that works.